This video we will study the instantaneous center of zero velocity. Okay. We will study how to locate the instantaneous center of zero velocity point. Okay, and we will use this point to determine the velocity of any point or rigid body in general plane motion. For any body undergoing planar motion, there always exists a point in the plane of motion at which the velocity is instantaneously zero. Okay, so this point is called the instantaneous center IC of zero velocity, and actually it may or may not lie on the body. Okay, and uh, if the locations of this point can be determined, the velocity analysis can be simplified because the body appears to rotate about this point at that instant. So if we focus on the equation that we already studied for relative motion analysis of velocity, we found that we can determine VB if we know the motion of the base point A, VB is equal to VA plus omega cross RB sub A. So for this case, if A is IC, that is instantaneous center of zero velocity, so then it means that at this instant, VA becomes zero. So VB is equal to omega cross RB sub IC as now. It is simplified the problem to be like this. Okay, so for the case that we know the location of IC, it is better to use the IC as the reference point for that instantaneous time. Okay, so how to locate the IC? Okay, to locate the IC, we can use the fact that the velocity of a point on a body is always perpendicular to the relative position vector from the IC to the point. Okay, so for the first case, okay, if we consider for the case that we already know velocity of point A on the body, and we also know the omega, the angular velocity of the body also. So in this case, IC is located along the line drawn perpendicular to VA at VA. We know is located along this line. That is the line that's perpendicular to VA. And the point is located at distance RA sub IC. That is can be determined by divided by the velocity of VA and omega. Okay, so then we now can determine the distance from point A. Okay, now we can locate IC. Okay, so for the second case, okay, the line of action of two non-parallel velocity VA and VB are known. Okay, so for this case, we know the line of action of VB and VA. Okay, all it's for this case, we know the directions of VB and VA. So for this case, we can find IC by construct line segment from A and B perpendicular to VA and VB. The point of intersection of these two line segments locate IC. So for this case, we draw the line that's perpendicular to VB, draw the line perpendicular to VA, and intersection point is IC. This is for the second case. For the third case is when magnitude and directions of two parallel velocity, okay, we have two velocity. That is, we know that it's parallel to each other. For this case, VB parallel to VA. Okay, and we know its velocity, but it's parallel to each other. The location of IC is determined by proportional triangle of this. Okay, we draw the line past to 2 points. Okay, and we have VA and VB, and we can find the IC by using proportional of triangle of two triangle that we can locate IC. This is for case that IC is between point A and B, and also for the case that IC is maybe not between point A and B, but we know that VA and VB is parallel to each other like this. Okay, so we can draw the line. We found that the line that we measure from A to any point. That's now actually we don't know now. Okay, but we just know only RA sub IC we may draw, and RB sub IC we may draw first, and we don't know this is equal to what. Okay, but we know the velocity, we know the magnitude of velocity VA and VB. Okay, according to this, we can draw the line that's pass to these two velocity. Okay, that is actually we know the magnitude of this, and we can determine RA sub IC and RB sub IC by the proportional of triangles. Okay, that is the location of IC should be here. Okay. So the velocity of any point on body undergo general plane motion can be determined easily once the instantaneous center of velocity of the body is located. Okay, and because at this point it is the point that at that instant the velocity of this point becomes 0. So the magnitude of velocity of any arbitrary point is become just only term of omega r. Okay, r is the radial distance from IC to the point, to any point. Okay, so this is the simplified method for the case that we know IC. Okay, and we can use for velocity only. So let's take a look at this example. A linkage undergoing motion as shown in the picture. The velocity of block D is known. It is equal to 3 meters per second. And we would like to find the angular velocity of link AB and link BD. Okay. So for this problem, we will starting with locate the IC first. Okay, because D moving to the right. Okay, so D moving to the right, we can draw the line perpendicular to D first. Okay, and the BA is moving has a rotation about fixed axis. So for this case, B should have the motion along this key line. So then if we draw the line that's perpendicular to the VB, we will have this line also. So it's found that we can locate point IC over here that is perpendicular to VB and perpendicular to VD. So for this case, we can find that for this case, RB sub IC is very easy to find from this picture that RB sub IC become 0.4 meter and RD sub IC become 0.566 meter. And according to this, we know VD. So for this case, we know that VD is equal to omega BD RD sub IC. And we can find that omega BD is become 5.3 radian per second counterclockwise. And if we consider for the link AB, we know that omega AB is become VB over RB sub A. And for this case, VB is equal to RB sub IC omega BD. And for now, we can determine for omega AB that is equal to 5.3 radian per second clockwise. That's complete this problem.